Now we need to look at extending everything we've been talking about with divergence, curl, and Green's theorem into R3 space. In two dimensions, the divergence gives us a measure of either expansion or contraction of a vector field at each point. The flux form of Green's theorem implies that if the two-dimensional divergence of a vector field throughout a simply connected plane region is zero, then the flux across the boundary of the region is also zero. If the divergence is non-zero, Green's theorem gives the outward flux across the boundary. So that when I'm in R3 space, these ideas extend so that the divergence is a measure of the expansion or contraction of a vector field at each point in the three-dimensional volume that I'm working with. Green's theorem also implies that if this three-dimensional divergence throughout my region is zero, then the flux through the surface of the region will also be zero. If the divergence is non-zero, then my outward flux across the surface is what is given by using Green's theorem. So in two dimensions, the divergence of a vector field F, defined by the vector with components f and g, is given by the partial of f with respect to x plus the partial of g with respect to y. In three dimensions, the divergence for my vector field, specified by a vector with components f, g, and h, becomes the sum of the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. Now we bring back my del operator. Remember that del is given by the partial derivative with respect to x in the I hat direction, the partial derivative with respect to y in the j hat direction, and the partial derivative with respect to z in the k hat direction, which I can write in component form as the components the partial derivative with respect to x, the partial derivative with respect to y, the partial derivative with respect to z. I write this as a vector, although it's not exactly a vector. But as an operator, we can apply this to either a scalar valued function or a vector field. If I apply the del operator to a scalar function f of xyz, I get a result which is the gradient of f of xyz, which is a vector. I can write this as del f is equal to the partial of f with respect to x in the I hat direction, plus the partial of f with respect to y in the j hat direction, plus the partial of f with respect to z in the k hat direction, or I can write it in a more concise form as a vector with the components f sub x, f sub y, f sub z. But if I take the dot product of this del operator and the vector field f, given with a vector with components f, g, h, we get something pretty interesting. Del dotted with f is equal to a vector with components the partial with respect to x, the partial with respect to y, and the partial with respect to z, dotted with a vector with components f, g, h, which gives me the partial of f with respect to x, plus the partial of g with respect to y, plus the partial of h with respect to z. This is the divergence of a vector field in 3D space. So the divergence of a vector field f specified by the vector components f, g, h that is differentiable on the region in R is given by div f is equal to del dot f, which is equal to the partial of f with respect to x, plus the partial of g with respect to y, plus the partial of h with respect to z, where div f is used to mean divergence of f. If del dot f is equal to 0, the vector field is source-free. Let's work an example. If I'm given a vector field f that's specified by a vector with components yz times sine of x, xz times cosine y, and xy times cosine z, let's find the divergence of the vector field. Div f is given by del dot f. So I'm looking for the partial of f with respect to x, plus the partial of g with respect to y, plus the partial of h with respect to z. In the case of my vector field, del dot f is equal to the partial of yz times sine of x with respect to x, plus the partial of xz cosine y with respect to y, plus the partial of xy cosine z with respect to z. This gives me yz cosine x minus xz sine y minus xy sine z. This is my divergence of my vector field. If I wanted to know the divergence at a specific, I would simply take the coordinates for x, y, z, plug those in here, and get a numerical value for the divergence of my vector field at this point in space. Now I want to talk about divergence of a radial vector field. Vector fields like f is equal to a vector with components x, y, z is one example of a radial field. These types of fields apply in many important and prevalent physical applications like gravitational fields or electromagnetic fields, and any field that obeys an inverse square law. We can generalize a result for divergence of radial vector fields in particular because they are so prominent in these important topics. So for a real number p, the divergence of the radial vector field f given by the vector r divided by the magnitude of r raised to the p power is equal to a vector with components x, y, z divided by the quantity x squared plus y squared plus z squared raised to the p over 2 power. This divergence is given by del dot f, which is equal to 3 minus p over the magnitude of r raised to the p power. So let's work an example. I'm given my vector field f, which is defined by the vector with components x, y, z, divided by the quantity x squared plus y squared plus z squared raised to the 3/2 power. I want to find the divergence of this vector field. F is given by my vector r divided by the magnitude of r cubed. This gives me my vector with components x, y, z divided by the quantity x squared plus y squared plus z squared raised to the 3/2 power. Del dot f is equal to the partial with respect to x of x divided by x squared plus y squared plus z squared, all raised to the 3/2 power, plus the partial with respect to y of y over the quantity x squared plus y squared plus z squared raised to the 3/2 power, plus the partial with respect to z of z over the quantity x squared plus y squared plus z squared raised to the 3/2 power. This gives me y squared plus z squared minus 2x squared plus x squared plus z squared minus 2y squared plus x squared plus y squared minus 2z squared, all over the quantity x squared plus y squared plus z squared raised to the 5/2 power. When I simplify this, I get 0. If I look at del dot f and use my formula that says that 3 minus p divided by the magnitude of r cubed, my p in this case is 3. I get 3 minus 3 in the numerator, so my other form of del dot f does in fact give me 0. I can also evaluate divergence by observation of a graph. I have a graph here that plots the vector field given by the vector components x and y squared, and I've placed a circle for my region with a radius of 2 centered on the origin. I also have 2 points marked inside my region. I have a point P located at the coordinates -1, 1, and a point Q located at coordinates 1, -1. So now, by observation of my vector field, the circle C and the 2 points P and Q, would you suppose the divergence is positive or negative at P and Q, and if so, why? I'm going to first look at my point P, and what I notice is that the arrows pointing away from this point are larger in magnitude than the arrows pointing in toward that point, so it would appear that at P the divergence will be positive because it's positive for an outward bound flux. At the point Q, the larger magnitude arrows are pointing toward the point, so that my divergence would be negative here. This is through observing my graph. I still want to do a calculation to see if I'm right. So now I'm going to compute the divergence at points P and Q and determine on what part of my circle C is the flux outward and inward, and I would like to know if the net outward flux across C is overall positive or negative. My divergence of f is given by the partial of f with respect to x plus the partial of g with respect to y. F is x and g is y squared, so that my divergence of f is given by 1 plus 2y. At the point P, which has coordinates of -1, 1, my divergence is 3, which is positive. So that at P, I have an outward flux. At Q, my coordinates are given by 1, -1. The divergence of F at this point is -1. Because it's negative, I have a net inward flux at the point Q. This confirms exactly what we thought would happen just by observing the vector field on this region. Now I want to evaluate the overall flux on my region C. The flux is outward above the line y = 1, and it's inward below the line y = -1. Overall, the size of the arrows pointing outward in this top region and the size of the arrows pointing inward in the bottom region are roughly the same in size. This means that these areas of vectors essentially cancel each other out in these two regions of C. So what I need to do is look at the remaining vectors left in my region that aren't being canceled. In the remaining arrows, all of these arrows are pointing outward, giving me a net positive outward flux in my region C. So now you get to try it. Pause the video, and given the vector field specified by a vector with components x, y, and z, multiplied by the quantity x squared plus y squared plus z squared is equal to r times the magnitude of r squared, calculate the divergence of the radial field. Express the result in terms of r and magnitude of r. When you're ready, restart the video to check your understanding. So the first thing I need to do is compute the divergence of my vector field. I want to find del dot f. Del dot f is the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. This means that I'm taking the partial of x times the quantity x squared plus y squared plus z squared with respect to x plus the partial of the product y times the quantity x squared plus y squared plus z squared with respect to y plus the partial of z times the quantity x squared plus y squared plus z squared with respect to z. This gives me 3x squared plus y squared plus z squared plus x squared plus 3y squared plus z squared plus x squared plus y squared plus 3z squared, which becomes 5x squared plus 5y squared plus 5z squared. I factor a 5 out, and I get 5 times the quantity x squared plus y squared plus z squared, which can be written in terms of the magnitude of r. This gives me 5 times the magnitude of r squared. In other words, my divergence is positive on this field. It tells me that my vectors on this field will all point outward from the center of my region to the outside. Be sure and let me know if you have any questions about working with divergence in R3 space.